The next article from the chapter Rotational Dynamics is the rotational motion of the body. Now in this article we have to discuss moment of inertia, kinetic energy of rotating body, torque acting on rotating body, physical significance of moment of inertia. This moment of inertia is analogous to the quantity mass. This is we have to prove. Now first is concept of moment of inertia. Let us consider a body of mass capital M. Let this body is divided into smaller and smaller particle. Let M1 is a mass of first particle, M2 is mass of second particle, M3 is mass of third particle, and so on and so on. Mn is a mass of last particle. These are the masses. We can write like this: capital M, which is the total mass of the body, is equal to M1 plus M2 plus M3 plus M4 plus Mn, which can be written like this. It is a summation of Mi. Okay. Now again let us consider this body is rotating about the axis passing through this point O. It is rotating in this sense with angular velocity omega and also angular acceleration alpha. In this case, the moment of inertia is a sum of product of masses, sum of mass and square of distance of that mass from axis of rotation. That is M1 R1 square plus M2 R2 square plus M3 R3 square plus M4 R4 square plus last is Mn into Rn square. This can be written in summation form, sum of Mi into Ri square. I is from 1 to n. This is the moment of inertia. Now from this it is clear that moment of inertia is the quantity analogous to mass, which includes not only a mass but also take care of distance-wise distribution of mass around the axis of rotation of the body. This is the moment of inertia. Just remember important point, this moment of inertia is depend on the distance of mass. This is the important distance of mass from axis of rotation. It is depend on the distribution of mass, that is distance of each mass from axis of rotation. This is the concept, actual concept of the moment of inertia. Now we will find next the kinetic energy of this rotating body and relation between this kinetic energy and this moment of inertia. This is our next article. Let us consider a body of mass M rotating about axis passing through point O. Here omega is the angular velocity. Let a body is divided into number of masses M1, M2, M3, M4 and so on Mn. Let R1 is a distance of mass M1 from axis of rotation, R2 is a distance of M2 from axis of rotation, R3 is a distance of M3 from axis of rotation, and similarly Rn is a distance of Mn from axis of rotation. Now to find the kinetic energy of this body, we will find a kinetic energy of individual particle and add up this all energies to find the total kinetic energy. Now see the kinetic energy of first particle having mass m1 is E1 given by E1 equal to 1 half m1 into v1 square. But see, but v1 equal to r1 into omega. Hence we can write this E1 equal to 1 half m1 into r1 square omega square, squaring both sides of this equation. Similarly, kinetic energy of second particle having mass m2 is given by E2, which is half of m2 into v2 square, which is equal to 1 by 2 m2 into r2 square omega square. Similarly, E3 equal to 1 half m3 into r3 square omega square, and so on. The energy of last particle having mass mn, that is mn rn square omega square. Now using this kinetic energies, we will find the total kinetic energy E equal to E1 plus E2 plus E3 plus last En. Now see, substituting the above equations, that is 1 half m1 r1 square omega square plus 1 by 2 m2 r2 square omega square plus 1 by 2 m3 r3 square omega square plus last 1 by 2 mn rn square into omega square. Now taking the common terms outside, that is 1 half omega square is a common term, that is constant. m1 into r1 square, m2 into r2 square, m3 into r3 square plus last is mn into rn square. Now observe the bracketed term. Now the bracketed term is nothing but summation of product of mass and square of distance from axis of rotation. I varies from 1 to n, which is nothing but moment of inertia. Hence the equation becomes 1 half omega square into I, or we can write the equation like this: energy equal to half of I into omega square. This is our required equation for kinetic energy of rotating body. This is our required equation for kinetic energy. Now in second article, we will find the equation for torque acting on rotating body. Okay. Consider a body of mass m rotating about the axis passing through point O. Let the body is divided into n number of particles having masses m1, second mass m2, m3, m4, mn. Body is rotating about axis with angular acceleration alpha. Now again let us consider r1 is a distance of m1 from axis of rotation, r2 is a distance of m2 from axis of rotation, r3 is a distance of m3 from axis of rotation, and so on. Last, rn is distance of mn from axis of rotation. Now see, when this body is rotating, a force is acted upon every masses. that is F1 is acting on M1. Similarly, F2 is acting on M2, F3 is acting on M3, F4 is acting on M4, and last we can write this Fn is acting on Mn. Now we will find the torque acting on each particle and then add up to find the total torque acting on the body. Now see, the torque acting on first particle is τ1, which is equal to F1 into R1, but this F1 equal to M1 into linear acceleration A1, and again adds this A1 equal to R1 into alpha. We can write this F1 equal to M1 R1 into alpha. Hence the τ1 equal to M1 R1 square into alpha, substituting the value of F1. Similarly, torque acting on second particle τ2 equal to F2 into R2. Similarly, we can write M2 R2 square into alpha. Torque acting on third particle R3 equal to M3 R3 square into alpha. Using the same equation, acceleration equal to R into alpha and force equal to mass into acceleration. Now last, the torque acting on last particle to n is Mn into Rn square alpha. Now we will find the total torque acting on the body. See, the total torque is τ, which is equal to τ1 plus τ2. Substituting these values, we will get M1 into Rn square alpha plus M2 R2 square alpha plus Mn into Rn square alpha. Now taking the common term outside the bracket, we will get alpha in bracket M1 R1 square plus M2 R2 square plus M3 R3 square, last Mn into Rn square. But the bracketed term is nothing but moment of inertia. Hence the equation becomes torque equal to I into alpha. Our required equation for torque acting on rotating body. Now see, our next and important discussion about the physical significance of moment of inertia. Now see, the equation for a torque acting on body τ equal to I into alpha, and similarly the equation for kinetic energy, which is equal to 1/2 I into omega square. Now compare these quantities analogous to the translatory motion. Now see, in translatory motion, this is the translatory motion. Here we will write in rotatory motion. Okay. Now in translatory motion, a physical quantity which is cause of the translatory motion, the quantity which produces the translatory motion is force, which is equal to ma, that is F equal to ma. For rotational motion, we have to apply the torque. We have to apply the torque to perform the rotational motion of body, which is equal to I into alpha. F equal to ma in translatory motion, τ equal to alpha I into alpha in rotatory motion. Similarly, the kinetic energy in translatory motion is given by half of m into v square. Kinetic energy in rotatory motion is given by half of I into omega square. Now comparing this equation, see. Now comparing these equations, force in translatory motion perform the same role as that of the torque in rotatory motion. Acceleration, which is rate of change of linear velocity. Alpha is angular acceleration, which is rate of change of angular velocity. These are the analogical quantities in translatory and rotatory motion. Similarly, this is the kinetic energy. Phi is rate of change of linear displacement, which is the linear velocity. Omega is the rate of change of angular displacement, which is the angular velocity. Here is the v square, here is again omega square. Hence, we can say that this mass and this I, or from this equation again we can prove m and I are analogical quantity. That means mass and moment of inertia are analogical quantity. That means m and I are same quantity. Mass and moment of inertia are same quantity, analogical quantity. Mass plays the role in translatory motion. Moment of inertia plays the role in rotatory motion. These both are the inertia. Mass is the translatory inertia and moment of inertia, that is I, is again rotatory inertia. From this equation, it is clear that, see, the equation for moment of inertia I is sum of mi into ri square. I is 1 to n, that is number of particles. From this equation, it is clear that the moment of inertia of an object depends on mass and second, the distribution of these masses about given axis of rotation. See, mass in translatory motion depend on only mass, but in rotatory motion this inertia depend on mass and also distances of this mass from axis of rotation. This is the physical significance of moment of inertia. Now in next article we will discuss two important theorems: principle of perpendicular axis and principle of parallel axis, to find the moment of inertia of bodies about different axes. Okay.